Is it recording? Hello?
Yeah, I started.
Okay. Good morning, everyone. I am Moinak Samanto, and today I'll be your host. I hope you're doing well. Today we'll have the second lecture of the foundational series on rings and modules by Srigyan Nandi. So without any further ado, let's begin. Over to you, Srigyan.
Yeah, thanks. I'll just begin sharing my screen. Yeah, could anyone tell me if my screen is visible?
Yes, it's very well.
Yeah, all right. Okay, so, oh God, gone far ahead in the talk. Yeah, so today's talk will basically build on the basic ideas developed in the previous talk. So I think in the previous talk, Sunshine introduced you to commutative rings with unity and several examples such as the formal power series ring and the polynomial ring, etc. And I think he also gave a brief introduction to ideals and adjoining elements. So today we are going to talk about the main part of this talk will be about two specific families of ideals known as the maximal and prime ideals. And then we'll also see a very famous theorem, or actually a famous version of the Hilbert's Nullstellensatz on the complex polynomials. And then we'll look into more special families of integral domains. And a lot of the latter part will consist of several results that will attempt to generalize basic number theory concepts of divisibility, primes, etc., to a more abstract setting. So I'll just do a quick recap of what Sunshine spoke on yesterday. I think this should take around 2 or 3 pages. So he defined a commutative ring with unity as a set R with two operations plus and the product. And the two operations were binary operations with the following properties. So, of course, we had that plus and the product are closed. Then we also had plus and the product are associative. Then plus and product are also commutative. In a general ring, it's not necessary that the product is commutative, but here I am in for this whole talk, the assumption will be that the rings that we are dealing with are commutative rings that have a unity. So the product is a commutative binary operations. So next, there exists a zero element in our ring such that uh, it is the identity for addition. That is, r plus 0 is equal to r for all r belonging to r. And we also have that addition is closed under inverses. So that is for all small r in the set R, we have the additive inverse also belonging to R, such that r plus minus r equal to 0. And since finally it's a commutative ring with unity, we have that the multiplicative identity should also be an element of this ring. So there exists one, the unital element that lies in R that satisfies the multiplicative identity property, which is 1 into R equal to R for all. So I mean, it may not be necessary, but I'll just give a small example for the sake of it. So, one such example of a ring would be the integers under plus and product, the standard addition and product. It forms a commutative unital ring. So, the integers under the standard addition and multiplication operations forms a ring. So I will not keep telling commutative rings with unity. I'll just tell ring from now on. So the next thing I want to recap is ring homomorphisms and isomorphisms. So a lot of these concepts are closely tied with the notions of vector spaces that you have learned in Algebra 1 and 2 in your first year. Oh, sorry, in Algebra 1. So uh, homomorphism is basically a map phi from two rings R and R dash. It's a function such that satisfies three properties. So the first is that the homomorphism respects addition. That is, phi of a plus b equal to phi a plus phi b for all a comma b in R. And the second one, naturally, it has to respect multiplication. That is, phi a b is equal to phi a into phi b for all a comma b in R. And the third one, which requires a bit more in-depth look at rings. It is a not so natural property, but it is a required property nonetheless. That is, phi should respect the multiplicative identity over both the rings. So phi should take the multiplicative identity of the first ring to necessarily the multiplicative identity of the second ring. So, as a trivial consequence, these definitions also imply that phi maps the additive identity of the first ring to the additive identity of the second ring, which is this statement. So, as you can see, it is very similar to, although not exactly similar to, it's quite uh, uh, in the likeness of linear maps in vector algebra, since it follows linearity and the conditions on linear maps also imply that the linear maps take 0 to 0. So here also we have that every homomorphism takes the zero element to the zero element. So just as we define the null space for a linear map in linear algebra, we define the kernel as discussed yesterday. So the kernel of phi is the set of all elements of the first string such that phi maps those elements to zero. And similarly, we define the image of phi, that is the set of all elements in the second ring, in the ring R dash, that are the image of some element in the first ring. So uh, as with any other algebraic object, a bijective homomorphism will be called a ring isomorphism. And although not immediately obvious, but pretty intuitive, if phi from R to R dash is a ring isomorphism, then it is of necessity that phi inverse, which exists since we defined phi to be an isomorphism, or if and only if it was bijective. So we have phi inverse from R dash to R is also a ring isomorphism between the two rings. So, and the third thing I would want to discuss is subrings and ideals before moving on to the main content of this talk. So, just like the definitions of a subspace or a subgroup, we have that if a certain subset S of a ring R satisfies the property that S under the same inherited operations of addition and multiplication also forms a ring, and the fact that the unital element of R also lies in S, then S is said to be a subring of R, which is a pretty intuitive definition. But we don't deal much with subrings in most of the commutative algebra that we do. So I'll just quickly give an example, and this is a very trivial example. I will not spend much time on subrings. So the same ring described in the beginning, Z plus product, is a subring of the same operations applied on R, which is a ring, and it is also a field. Some of the main subsets of rings that we are rather more interested in while doing commutative algebra and module theory are actually ideals, which do not have a very constructive or intuitive definition, but we'll see later why they're so important. So, if we define an ideal I to be a subset of R that satisfies the following two properties. So the first one being if A and B belong to I, that should imply that the sum A plus B belongs to I. So this can be thought of or summarized concisely by thinking of it as I is an additive subgroup of R. So addition is closed in I. And the second one is if A belongs to I and R belongs to R, that will mean AR belongs to I. This is a much less natural property, but it, if you are familiar with group theory, you can see its vague familiarity with normal subgroups. And that is the key reason why ideals are very important in the study of rings and modules. So these are similar, they play a similar part to what normal subgroups play in groups. So if I is such a subset that is closed under addition and also has the property that for any A belonging to I and any R belonging to R, AR belongs to I, then I is said to be an ideal of R. So one of the most common examples of an ideal arises from any ring homomorphism. So if phi is a ring homomorphism from R to R dash, then we always have as a necessary byproduct that the kernel of phi is, which is the set of all elements of R that get mapped to zero under the homomorphism, that the kernel of phi is always an ideal of R. It's a very trivial fact, which I will not prove. And throughout the talk, there'll be several more of such very elementary trivial facts, which I will not bother proving since they're very simple. So, another example of an ideal, to give a straightforward example of an ideal, uh, we can consider the ring, well, let's say, yeah, let's just take the same ring. In the ring of the integers, the subset taken by 5z, which is basically all the multiples, all the integral multiples of 5. So that is a such that a lies in the integers and 5 divides a. So we're basically looking at 0, 5, minus 5, 10, minus 10, so on. Is an ideal. This set forms an ideal of Z, of the ring Z. In fact, uh, we can even generalize this. Yeah, let's generalize this because that will be important for the coming few theorems that we will be doing. So, and again, I will not prove this generalization since it's a very trivial one. Every ideal of the ring of integers is of the form nz, where n is some natural number. Right. So, as you may have seen in the last talk also, an ideal, although being a separate subset of a ring, it need not be a subring on its own. In fact, an ideal is almost never a subring. And it can easily be seen why. Because if an ideal was a subring, then it has to contain the multiplicative identity of R. But if it does, then from the second property, we have that for any R belonging to R into 1 should belong to I, which would imply I is R. So if so, then we have that if an ideal is a subring of R, then it is the whole ring R itself. So no other ideal of R is actually a subring of R, since no other ideal of R contains the multiplicative identity. So now we can prove our first few trivial lemmas about ideals. And the first one being that in any ring R, we have the two trivial ideals, which is the ring R itself, as described previously, and the zero ideal. So this is very simple to prove. We have that both R and 0 are closed under addition, which satisfies the first requirement for being an ideal. And the second, we prove in two steps. So for any R dash belonging to R, we have R dash belongs to R for all R belong to R. So this is the second property of an ideal, and it is being satisfied for R. And for the case of the zero ideal, we also have for any R belonging to R dot zero is equal to zero itself, which again belongs to the zero ideal. So it is obvious that R and the zero ideal are ideals of R. Secondly, if an element A belongs to R, then another a very important family of ideals that we can generate are the principal ideals, which has been discussed before too. So it is the set of all elements that are expressible as R into A, where R is any arbitrary element of the parent ring. So we prove that this is an ideal. So we consider the set capital R into A, which is the set as described before of all elements expressed as RA, where R is an element of capital R. So if R1A and R2A belong to RA, then R1A plus R2A equals to R1 plus R2A. And R1 plus R2 is again an element of R. So this also belongs to RA. So it's closed under addition. And if R1A belongs to RA and R belongs to R, then we have R into R1A is equal to R1A, and R1 again belongs to R. So this belongs to R. So the second property is also satisfied, and therefore RA is an ideal. So just to emphasize, such ideals are known as principal ideal. And these are a very important family of ideals, and we will be seeing their applications later on in the talk. They are known as principal ideals since they are practically generated by one element. In this case, it was A. But I will not use the word generated much since we don't really have a rigorous definition of what it means to be generated by a certain set. But we'll use it as a loose term since they are generated by a single element. Okay. So now these principal ideals have a separate notation, and when we talk about a principal ideal generated by a certain element A, then we put A in the round brackets to denote that it is the principal ideal generated by A. And this is very similar to the basis notation for vector spaces, where if you have a certain list of vectors that forms the basis of a vector space, then you put the basis elements in round brackets to express that it is the basis of that certain vector space, and the basis generates the vector space. Similarly, although this is not a unique notation just used for principal ideals, we can use it for ideals generated by multiple elements. But to get to there, we first have to know what it means to generate an ideal, or precisely what it means for a certain subset of a ring to generate an ideal, which we do right now. So we talk about the ideal generated by a certain arbitrary subset of a ring. So if capital A is a subset of R and it is any arbitrary subset of R, then we consider the set IA given by all finite all finite R linear combinations of elements of A. That means we take finite from the arbitrary set A, we take finite elements at a time, and we calculate their R linear combinations. So this is all finite R linear combination. And this set of all the finite R linear combinations is, we give it the name I subscript A. And then we denote, and then we have the following theorems. We have that IA is indeed an ideal of R. So the intuitive definition that we have given for an ideal to be generated by a set, that is indeed an ideal. So again, the proof of this is elementary, and IA is said to be the ideal generated by the subset A in R. And also incidentally, as we would expect, IA is the smallest ideal of R that contains A. So now we have a strong definition of what it means for an ideal to be generated by a certain subset of a ring. So using this, we can move on and prove two very important theorems. So the first being that if F plus and F under plus and product is a field, then F has exactly two ideals. So in case people are unfamiliar with what a field is, although you may have come across the term in most probably in your real analysis one course, since R is a field, we'll just define it here. So a field is basically a commutative ring with unity that is, oh, so a field is a commutative ring with unity that is also closed under multiplicative inverses. Multiplicative inverses for all non-zero elements. So a field, basically, you can think of it as a ring that has the whole package. It has perfected and basically maxed out on all its settings. Since it forms an abelian group under addition, meaning it is closed under addition, it is closed under additive inverses, it is commutative under addition, and it's associative. And a field also has all the properties for multiplication over its non-zero element. So it's obviously commutative, it's closed, it's associative, and in this case, it is also closed under inverses. So it has everything. So some fields include, uh, well, the basic examples are the complex numbers, the real numbers, the rational numbers. So these constitute some of the fields. So it would be helpful to think of a field as the perfect ring in some sense, because it satisfies all the properties, all the neat properties for both the binary operations that it relies on. So I will repeat the statement of the theorem again, and then we'll go to its proof. So the theorem basically tells that if F is a field, then F has exactly two distinct ideals. And we have already discussed that any non-zero ring has two ideals, which are namely R and 0. So in this case, obviously, assuming the theorem holds, then the two ideals that are being talked about in the second argument are precisely F and the 0 ideal. And now we'll go to the proof. And this is a very important theorem that will be used to prove the Nullstellensatz. So we'll first prove the one way. So let I be an ideal of a field F. So if I is not equal to 0, we can consider the case where I is not equal to 0. That means there should be some A that belongs to I where A is not equal to 0. Because if if there was no A, such that A is not equal to 0, that means 0 is the only element of the ideal, which means the ideal is the 0 ideal, which is contrary to our hypothesis. So now, if A is not equal to 0, and since F is a field, we know that A inverse also belongs to F. So therefore, we can conclude that A inverse belongs to F, which implies that A inverse A equal to 1 also belongs to the ideal. Since A belongs to I, and A inverse belongs to F, and this follows from the second property of ideals. So we have that 1 belongs to I. So therefore, we can again apply the second property for any F belonging to F. F into 1 will belong to I, and which implies F belongs to I, which implies the ideal is equal to F. Okay, so that this basically tells us that if the ideal is not equal to 0, that implies the ideal is equal to F. So the sorry, so that implies the only two ideals are F and 0. All right. Now we can go ahead and prove the converse, the other direction of the proof. So we assume that F has exactly two distinct ideals, right? So let I be an ideal of F. And again, we make the same hypothesis assumption. So since F has exactly two distinct ideals, and we have already discussed that they should be either one of F or 0, we can assume that I is not equal to 0, as assumed before. So again, we can come to the same conclusion that I is equal to F. And since the only two ideals in this case will be F and 0, and if I is not equal to 0, then I has to be equal to F. So that will imply that there exists a non-zero A, the such that A belongs to I. And if A belongs to I, then the ideal generated by A will also lie inside I. So the ideal generated by A will be contained inside I, since A is an ideal. And this will imply that A is equal to F, which will imply that 1 belongs to A. And oh, my bad. Which implies that 1 belongs to A. So that implies there exists A inverse in F. So that A inverse equal to 1, which implies F is a field. Since all we required to prove that F was a field is that any non-zero element has an inverse, which we have shown. We took an arbitrary non-zero element A and we showed that there exists an inverse for A. So this gives the proof. So the proof of the theorem is complete, and it gives a very strong connection between two unlikely cases, which is F being a field and F having exactly two distinct ideals. So now we prove a trivial corollary of the theorem just proved, and which is again a strong corollary in its own right. That is, any homomorphism from a field to a non-zero ring is injective. And we start by assuming the existence of a homomorphism phi. So let phi be a homomorphism from a field to a non-zero ring, be a homomorphism. So as we know, the kernel of phi is an ideal of F. But we just proved that the field F has only two ideals because since it's a field and any field has only two ideals, which are the zero ideal or the entire field F. So we have, since kernel of phi is an ideal, we have kernel of phi is 0 or kernel of phi is equal to f. Well, we consider the case kernel of phi equal to f. So if the kernel of phi is equal to f, that will imply that phi of f is equal to 0 for all elements of f, which implies that phi of the unital element of f is also equal to 0. But since phi is a homomorphism, as discussed before, we know that phi should respect the unital elements. That means phi of the unital element of f should be equal to the unital element of r. But here we have shown that it is equal to 0. So, and we know 1r, the unital element of r is not equal to 0 since it's a non-zero ring. So this gives us a contradiction. So we come to the conclusion that curve phi is not equal to f, which implies curve phi is the only other viable choice, that is 0. Curve phi is the zero ideal. And as a trivial corollary, as you have seen in linear algebra, that if the null space of a linear map is only contains 0, then the linear map is injective. Using similar methods of that proof, we come to the conclusion that phi is injective. Since here the kernel of phi is analogous to the null space of a linear map, and the kernel of phi here contains only 0. So phi is injective, is necessarily injective. Okay. So now that we have defined ideals, let us see what we can do with ideals. And the next segment will make it a bit more clear why ideals behave analogous to normal subgroups. So there's not much to write in this segment. So we assume I is an ideal of R, and we denote I plus A to be the set of all elements expressible as I plus A, where I is an element of the ideal. So this has many analogs that you may have seen in group theory, and that is in group, if you have a normal subgroup, then this is an analog of Gn, where G is an arbitrary element of the parent group. Otherwise, in the study of vector spaces, this is more or less analog to the definition of an affine subspace. So if you consider R3 and you consider a plane lying on the xy axis, this is more or less equivalent to the shifts of the plane along the z axis, or creating the affine subspaces of the vector space. So I plus A denotes, you can think of I plus A as shifting the entire ideal AI by an element of size A, if that suits your, if that convinces you. So, and I plus A is a well-defined set for every A belonging to I. So now we can talk about the collection of all these shifts, and we denote that by the quotient R by I. So the collection of all these shifts, basically quotients R over I. So the R by I denotes all the collections of the form I capital I plus A, where each A, where each I plus A represents a shift of the ideal. So now, of course, it is not necessary. I will emphasize it here. It is not necessary that if A is not equal to A dash, that will imply that I plus A is not equal to I plus A dash, as we will see in the following note. So we can have cases where A plus I is equal to B plus I, and that we can even establish a sufficient condition where where the following happens. So if A plus I equal to B plus I, and here I is the capital I, that means which belongs to A plus I, since A here is equal to a plus 0 and 0 belongs to I. So a belongs to a plus I. So since we have a belongs to a plus I, that means a also belongs to b plus I, which means a can be expressible as the form b plus I, where for I is some element in capital I, and that will mean a minus b is equal to I, and that which basically means a minus b lies in capital I. In fact, this is both a sufficient and necessary condition, which I'll just mention. It is both sufficient and necessary for a plus I being equal to b plus I. Okay. So now that we are a bit more familiar with the quotient uh, of the ring over an ideal, which is the set R by I, we can actually just like we do in groups and vector spaces, we you might have guessed that we can define an addition and multiplication on the quotient, and that is again given by the intuitive definition that a adding a shift by a. Wait. Yeah. So adding a shift by A to a shift by B is gives the addition of gives the result of a shift by A plus B. So the addition, this is how the addition operation is defined. So A plus I plus B plus I will go to A plus B plus I. And similarly, the multiplication will also be defined in the similar intuitive fashion, which is A plus I into B plus I goes into AB plus I. So we can also check that these operations are well defined. So what do we mean by well defined? That is, we know that a plus I does not have a unique representation. A plus I could be equal to a dash plus I for some other a dash, and so could b plus I be equal to b dash plus I. So when we encounter situations like these and we define binary operations, we have to be sure that these operations are well defined. So to be well defined means if a plus I is equal to a dash plus I and b plus I is equal to b dash plus I, then we must have by necessity that a plus b plus I should be equal to a dash plus b dash plus I, and a b plus I should be equal to a dash b dash plus I. And again, this is another elementary result, so I will not be proving it here. So we can just assume that these operations are well defined. So if you had to take any other reason to convince yourself, you could, and if you've attended the group theory talks, these are the proofs will go along the exact same lines of the ones used for normal subgroups, and even more so for affine spaces over a vector space. So there is pretty sufficient convincing reason to not carry on with doing the proof. So we can move on from here. And now it it is fairly obvious that these operations on the quotient make the set R by I a ring. So from R, we and using an ideal, we have constructed another ring R by I, and this is again shows a strong similarity to normal subgroups, where if G is a group, if G is a group and N is a normal subgroup, then we can make the quotient group G by N, which also forms a group under the same operation. So this ring R by I is called the quotient ring of R over N. And we can define, since we create R by I from I, it would be very natural to provide the extension or yeah, to provide the extension to provide the extended ring with a homomorphism that can be used to represent the elements of R on the quotient ring R by I. And we do this using the canonical quotient map, which was also discussed yesterday. And the canonical map, which is always denoted with the letter pi, it takes R to R by I by taking every element of R to the shift of I by that very element R, a pretty natural map to have. So at this juncture, we again just state two elementary results without proving them. The first being if phi is a ring homomorphism from R to S, then we have the following. if J is an ideal of S, is an ideal of S, then phi inverse J. Here we are not guaranteed the existence of an inverse function, but we use the standard definition when we apply functions on sets rather than individual elements. So phi inverse J is given as all the R such that R belong to R and phi of R equal to J. So phi inverse of J, if J is an ideal of S, is also is an ideal of R. So a bit more on this. We call this the contraction of J. So, and the second one is less intuitive one. So, since we saw that the contraction of an ideal via the inverse of a homomorphism preserves the fact that it is an ideal, it would be natural to think that, well, the homomorphism itself should preserve the fact that it's an ideal via extension. And however, that is not true always. And it is very trivial to see when your map is not surjective. So there are very easy examples that one can construct without a surjective homomorphism where the extension of an ideal does not is not preserved as an ideal. So we come to the following theorem with an extra constraint on the map, and that is if phi is surjective and I is an ideal of R, then phi of I equal to S such that S belongs to S and there exists R belong to R so that phi of R equal to S. This set, which is basically the image of the ideal I, is an ideal of S. So if I have two rings, R and S, and I have an ideal I, the image of this ideal, it need not be an ideal in S. And it is an ideal only if the map is surjective. It is not an if and only if condition. There are non-surjective maps that still preserve certain ideals, but it is not surjective in the general case. So it is not an ideal in the general case. So not necessarily an ideal. However, on the contrary, if we had an ideal J and this being S and this being R, then the contraction of J to subset I would make the subset I an ideal of R, and that is necessarily an ideal of R. Okay. Now that we have these two things, we will just take a quick recap of the two isomorphism theorems that we came across yesterday. And I will not prove these. If you have attended the talks on group theory, then the proofs should carry on along similar lines and should be fairly simple. But even still, it's not really necessary to prove these theorems. Even without a fair background in group theory, these are pretty simple to prove. So we start with the first isomorphism theorem. So it assumes that phi is a homomorphism from a ring R to a ring S, and it states that capital K is the kernel of phi. And we assume that I is an ideal contained in the kernel. The kernel itself being an ideal, we assume that I is a smaller ideal contained inside the kernel of R. And then we consider the quotient map defined before, the standard quotient map, which takes an element of R to the ideal shifted by R. So it's a theorem in two parts. So the first one is the general case. If I is any ideal contained in K, that is, if I is a subset of K, then there exists a unique induced homomorphism from R by I, the quotient map to the quotient ring to S. So it is far easier to state these in terms of commutative diagrams. So if R is a ring with the homomorphism S phi from R to S, we also have R by I as our quotient ring with the natural quotient homomorphism, which is phi. So what the theorem states that is, given these two homomorphisms and these two rings that are both extensions of R, it would be natural for us to think that yes, there could be a homomorphism, or rather a natural homomorphism from one extension to other another, and the first isomorphism theorem guarantees the existence of that extension, and that also follows a neat composition of both the uh, maps pi and phi, and that it defines to be the map phi bar. So it says that there exists a unique phi bar from R by I to S, such that phi bar is the phi bar composite of pi is equal to phi. So it guarantees the existence, and it states that this will be a homomorphism. So it will be a homomorphism. And this is for the general case where I is any ideal contained in K. Now, for a specific case, if I is equal to the ideal, if I is equal to the ideal K, which is the kernel of phi, then the phi bar defined above is not only a homomorphism, but is also an isomorphism. So here, what we get is that we get that the when R is quotient where when R is quotiented over the kernel of phi, it is isomorphic to the image of phi. Of course. Oh, I forgot to mention here that phi should be a surjective homomorphism in this case, because we may not always map to the whole of S. We may map to the image of S. So in either case, a lot of elements of S will be left out. So this one, we must assume that phi is a surjective homomorphism. Homomorphism. All right. So now we can move on to the second isomorphism theorem, and that states that again, it builds on the same conditions given. It assumes that phi is a surjective homomorphism from the ring R to the ring S, and again, the kernel of phi is K. Then it states that there is a direct bijection between all ideals of R containing K and all the ideals of S. And we also have that when I is an ideal of R that contains K, then R quotiented over I is isomorphic to S quotiented over phi of I. So let's try to visualize the theorem a bit, although there is very limited stuff that we can do. If R is a ring and it has the kernel K, we consider any arbitrary ideal that is contained in K given by I. And what we have is that there is this can directly correspond with any ideal of S. So there is a direct correspondence between all the ideals of S and all the ideals that contain K in R. Although this is a very bad diagram, just as the last ones. I it should give a graphical image of basically what is going on. And R quotiented over each of these ideals is isomorphic to one S quotiented over the image of these ideals. So as you would guess, this bijection is actually given by phi. So this bijection is also induced by phi. So if I is an ideal of R containing K, let's say I, then it is taken to an ideal of S given by phi of I. And we know that phi of I is an ideal of S here since we assume that phi is surjective, which was a required condition in the previous theorem. So as in most cases in algebra, when we require a bijection, it is induced by the already present ambient homomorphism, which in this case is phi. So I think we've covered most of the basics that we need over here. So we can move on to the notion of a fraction field. So yeah, so if R is an integral domain, and as you know, okay, so let's just remember what an integral domain is. An integral, oh, that's the wrong notation. An integral domain is a ring such that if AB equal to 0 in the ring, that should imply that either A is equal to 0 or B is equal to 0. That is, this ring contains no zero divisors. So contains no zero divisors. Yeah. So if R is an integral domain and oh, okay. So my bad. I already mentioned what an integral domain is over here. So okay. So then it would be natural to think that given any ring, one can actually extend it such that the ring again forms a field because a field is something which in a sense you're always looking for since it satisfies all the nice properties. So and this is true, but only for a specific family of rings, which are the integral domains. So we can indeed construct a field, an extension field of R, which is called the field of fractions, denoted by Q of R, since Q stands for the rationals, and we're going to construct fractions here. So, and the constructed field is also the smallest field containing R up to isomorphism. So I'll explain what that means. Basically, we can have two different fields containing R. So if F1 and F2 are two different smallest fields containing R, then F1 should be isomorphic to F2. This is what it should be. This is what it means to be smallest up to isomorphism. And of course, here smallest is with respect to inclusion. So if F is the smallest field containing R and G is any other field that contains R, then there is an injection from F to G, which means F has a copy that is contained in G, which means F is smaller than G. So we'll attempt to give this construction, and it's a very elegant construction also. So first we will define q dash of R to be equal to the set of all ordered pairs of the rings such that A and B belong to R and B is not equal to 0. So from this, you can already see where we are going. This is very similar to the extension of Z to Q. So by B not equal to 0, we already get the hint that what we're trying to do here is make fractions. So these ordered pairs actually represent fractions, but there is some more work that has to be done to get a concise definition. So we define an equivalence relation tilde on this Q dash of R. So we define AB to be related to CD in Q dash of R if and only if AD equal to BC in R. This again is natural since just by defining ordered pairs we cannot have distinct fractions. For example, in Z, I use a different color for this. In Z, if we define the same ordered pairs and we define the Q dash of Z, we could have the ordered pair 1, 2 and also 3, 6, which although are distinct, we would like them to be equivalent since we want them to represent the same fraction. So we first define an equivalence relation that partitions Q dash of R and partitions similar ordered pairs into similar equivalence classes. So now now that we have the relation tilde, we know that tilde is also an equivalence relation. Equivalence relation. Now we define, we can begin defining the fractions. We define A by B to be the equivalence class of AB in Q dash of R. Yeah. So now that we can define the fractions, we can define the fraction field U of R is equal to the set of all such equivalence classes A by B such that A comma B belongs to Q dash of R. And now that we have defined these equivalence classes, it is already, we are just a very few steps away from formally constructing it as a field. Now that we have the required elements, we just have to show that the operations of addition that we defined hold, so do those of multiplication. And then we just have to clearly define an inverse, both for addition and multiplication, and an identity. So we define the equivalence class A by B plus equivalence class C by D to be equal to, as would be natural, AD plus BC by BD. And similarly, the equivalence class A by B into that of C by D to be equal to AC by BD. So why, you might think, why did we require that R is an integral domain? I mean, so far what we did, we could have done with any ring R. But the problem lies exactly in this definition of addition and multiplication. When we take two non-zero re- denominators, D and D, we must be assured that in the sum and the product, the denominators will again remain non-zero. And this can only be guaranteed if it is an integral domain. So this is why we can only perform the field extension on such integral domains. So now that we have defined addition and multiplication, we have that 0 by 1 is the additive identity for this, and 1 by 1 is the multiplicative identity for this. And we have that the inverse of A by B is given by the equivalence class of B by A. So we have that Q of R is a field and is in fact the smallest field. And it is very trivial to prove that it is the smallest field up to isomorphism that contains the integral domain R. All right. So now I think you have been told about the ring of polynomials yesterday, but there is another additional fact about these rings that we will have to exploit, and that is a generalization of the polynomials over the reals and the complex numbers, which is namely the division algorithm in such polynomial rings. So now our main aim in this slide is to generalize the division algorithm for arbitrary polynomial rings, which although cannot necessarily be done, but we will get a sufficient extension that will help us prove many more important theorems later on. So we start with the standing assumption that R of X is an arbitrary polynomial ring over one variable over the ring R. So now the division algorithm states that we want it to be as neat as the one we have for polynomials over the reals and complex, and we do in turn get something that neat. In fact, we get the exact same thing with a minor caveat. So if fx and gx belong to the polynomial ring, but here is the caveat. We require that the divisor f of x must be monic. So such that fx is monic, then we follow on with the usual division algorithm. There exists unique q of x and r of x that lie in the polynomial ring x, such that g of x equal to fx qx plus rx, where Rx is either equal to 0 or the degree of Rx is less than the degree of f of x. So this is the standard division algorithm, except with the one caveat that this holds only when, not only, this holds if the divisor is monic. Because when we do not have a monic divisor, it means the leading coefficient of the divisor could be a zero divisor also. And this actually hinders the division algorithm. So it is better to keep the uh, uh, divisor monic, although a more sensible generalization would be to have that generalization would be to have that leading coefficient of divisor, that is f of x, must be a unit. That's yeah. So this would be a more sensible generalization to have. It must be a unit. Since it being one and it being a unit, there is no difference between the two cases. Since units in R are literally no different from the unital element of R. So it must be a unit, and unit is that is U belongs to R, and there exists an inverse for U in R, such that so that U inverse equal to 1. Anyway, but it makes no difference to consider just monic f, because given any f, you can multiply it by a scalar which takes the leading coefficient to that unit. So we will just use this version of the division algorithm in which the divisor is a monic polynomial. So finally, we have enough material to come to the definition of maximal ideal. And here is where the stuff gets a bit intense, and one even has to go to the famous or celebrated axiom of choice or Zorn's lemma to prove certain concepts in this. So we first start with the notion of a partially ordered set. So, as you may guess, a partially ordered set is a set with a relation less than or equal to, and this relation satisfies three properties. The first one being it is transitive. So, if A is less than equal to B and B is less than equal to C, then A must be less than equal to C. So, that is transitivity. And A must be less than or equal to A. So that's obvious since A is equal to A. I think this was called reflexivity. Yeah, this is the reflexivity. And A less than B, A less than equal to B and B less than equal to A should obviously intuitively imply that A is equal to B. These three define a partial order. Uh, there's a reason it's called a partial order because none of these three rules, even taken together, guarantee that any two elements can be compared. So something a set such as the integers, or let's just take the natural numbers, 1, 2, 3, so on. In this, the natural order allows for comparison between any two elements. So if you have n and if you have m, you will always have one of n less than m, or n greater than m, or n equal to m. But here, none of these three rules guarantee that any two different elements can be compared. That's why it's called a partial order. So, I mean, to get a better understanding, we can just take an example of a partially ordered set, which does not happen to be totally ordered. And one of the most classical examples is take all rectangles on R2, right? And the order is, as you may have guessed, inclusion. So one rectangle is lesser than the other if and only if it is completely contained in the other rectangle. So let's just try to draw this to get a better understanding of what arbitrary partially ordered sets look like. So we have R2. I'm not going to draw the axis. It will be much better to just draw a plane or a piece of paper. We didn't even need R2. So we could take the set of all rectangle 1, rectangle 2. I mean, there are uncountably many rectangles. But look at this. If we have rectangle 1, rectangle 2, then we have 1 is less than 2 over here. Clearly, because 1 is contained in 2. Similarly, if this is rectangle 3 and this is rectangle 4, we have 4 is less than 3, right? However, I really cannot compare 1 and 3 over here. There is no scope for comparison between 1 and 3. Although this still satisfies the rules of a partial order. That is, the first one, if a rectangle is contained in a second rectangle and the second one is contained in the third one, then it is of necessity that the first one is contained in the third one. Similarly, every rectangle is contained in itself, and if two rectangles contain each other, then they are one and the same. This is still a partial order, but it does not give the scope for direct comparison of elements. So we try to bring in the notion of a total order into this partial order without changing much. So we define something called a chain C in a partially ordered set. And a chain is a subset of P such that any two elements can be combined. So again, considering the same example, we have that the set of all rectangles that are sequentially contained in another forms a chain. Since in this chain, since in this set of rectangles, each either for any two rectangles, we either have one is contained in the other or the other is contained in one. So there is always scope for comparison. So a chain in a partially ordered set P is a subset in which is a totally ordered subset when inherited with the same relation. So and we can trivially see why it's called a chain also, since these are since in most partially ordered sets they look like a sequence of sets that each contain each other, leading to an ascending staircase or an ascending chain. So now that we are familiar with what a partially ordered set is and what a chain is, we come to one of the most fundamental theorems that we will be using for this section of the talk. And that is Zorn's lemma, which, as some of you may know, it is an equivalent. It is one of the more famous equivalents of the axiom of choice. So, what does the Zorn's lemma state? So, it basically says that let P with the relation less than equal to be a partially ordered set such that it has an extra property, which is every chain C in P has an upper bound UC. So if we go back to the previous example, and if we take the whole plane R2, then there is no real upper bound for the any chain of rectangles. Since for any rectangle, you can keep getting a rectangle greater than the said rectangle. However, if we restrict ourselves to the finite plane or let's say a space contained by a bounded rectangle, then the condition holds. Since no matter what chain we have, we are all finally bounded by this larger rectangle, which is the space itself. So we in the basis of Zorn's lemma, we consider partially ordered sets such that every chain has an upper bound in the partially ordered set. Then Zorn's lemma states that if the partially ordered set satisfies this condition, then P must contain at least one maximal element. And a maximal element MP is an element in P such that there is no other element in P that is greater than the maximal element. So let's see how this applies to rings. So we define something called the maximal ideal among the set of all ideals. So let R be a ring and let M be an ideal. M is called a maximal ideal if M is properly contained in R, that is, M is not R itself, and the only ideals of R that contain M are M and R itself. So basically, of course, if we wanted a maximal ideal, it would be very trivial just by setting the maximal ideal to be R, because R contains every ideal. So there can be ideal that properly contains R. So we try to get we disregard this choice of maximality and instead go for the next best thing that we can hope for, is that we have R and we have this apart from R and the ideal itself. Is called a maximal ideal in R. So now we used all these previous notions of partially ordered sets and chain to come to this very nice proof that states that every non-zero commutative ring with unity has at least one maximal ideal, although which may not be very obvious, right? So the Zorn's lemma helps us a lot by proving such I wouldn't say counterintuitive, but neither is it a very intuitive statement. So, and the proof is simple. Once we have the powerful statement of the Zorn's lemma, and that is let P represent the set I such that I is an ideal properly contained in R. So if R is the ring, P is the set of all ideals that are properly contained in R. So all ideals that are not R. So we have this to be the set P. Now, second, we can order P by set inclusion. That is, I1 is less than or equal to I2 if I1 is fully contained in I2. Again, this is a partial order. We may have two ideals such that neither one contains the other. This is why we use a partial order, right? So, and then consider any chain I alpha. Alpha belongs to the indexing set alpha bar in P. So if R is a ring, our chain will look like ideal I1 contained in I2, contained in I3, and so on. Because in this chain, there is a scope for direct comparison between any two given ideals. So then we have the theorem states that if we want a maximal ideal in the among the sets that you have considered, we need to be able to find an upper bound for any one of these chains. Of course, the upper bound can't be the ideal R itself, since the set we are considering does not contain the ideal R. It only contains the ideals properly contained in it. But we can easily get around that by considering the ideal I to be equal to the union of all the ideals that we considered in the chain. So we can, okay, so from this, we can see that I alpha, for every ideal in this chain, I alpha is contained in either union. So I alpha is contained in I. And again, this is a rather elementary proof, which I will not be doing. The union of all these ideals in the chain is also an ideal. So I equals to this union is also an ideal. Therefore, I is an upper bound for this chain. So we have that every chain in this set has an upper bound. Therefore, every chain in P has an upper bound. So every chain in P has an upper bound. And therefore, P must contain at least one maximal element. Therefore, P must contain at least one maximal element. And that is some M, and this will be a maximal ideal. So this is a very beautiful proof from the Zorn lemma, which again follows from the axiom of choice. And this guarantees that such ideals, such maximal ideals following the maximality property do indeed exist for any ring R. And they're not specific only to certain rings R. So now that we have that, let us prove some elementary, let's get back to proving some elementary results again. So let's see. So let's see what to prove. So let's consider a surjective homomorphism. Uh, Theta from a ring R to a field F. So theta is from a ring R to a field F. So we have the second isomorphism theorem. The second isomorphism theorem, which stated that the ideals of F will be in direct bijective correspondence with the ideals of R containing kernel of theta. This was the statement of the second isomorphism theorem. So they have a bijection between them, right? So now F is a field. F is a field. This gives some very nice restrictions. So the only ideals of F are F and 0, as we proved before. The only ideals of a field are F and 0. Therefore, since the ideals of F are in direct correspondence with the ideals of R containing kernel of theta, that means there are only two ideals of R that contain kernel theta. So there are only two ideals of R containing kernel theta. But as we already know, kernel of theta is an ideal. So kernel of theta must be one such ideal. So that is kernel of theta. And the other one, of course, is R itself. So kernel of theta and R are the only two ideals that contain kernel of theta. So here, is this not the definition of a maximal ideal? Since no other ideal properly contains kernel of theta and is also properly contained in R. So therefore, kernel of theta is a maximal ideal. So this basically says if we have a surjective homomorphism for any surjective homomorphism, in fact, from a ring R to a field F, we have that the kernel of that homomorphism is in fact a maximal ideal in R. So now let's try proving a similar thing and develop both the converse and the forward condition of another strong theorem. So now, if M is a maximal ideal of, we consider the quotient map phi from R to R quotiented by M. Of course, you can do this since M is a maximal ideal, which means M is of course an ideal, and you can always quotient by ideals. We will represent this by R dash. So we have that the kernel of pi is equal to all elements in of width is equal to all elements belonging in R such that pi of R equal to 0, which basically implies R plus M using this ideal operation, meaning the ideal shifted by R is equal to 0. But that is the same thing. 0 in the quotient ring is the same thing as, oh, wait, yeah. 0 in the quotient ring is the same thing as 0 plus M, which means that R minus 0 belongs to M, which same thing as R belongs to M. So kernel pi is equal to M, right? So we have this. So again, from second isomorphism theorem, we use the same theorem and prove the following. There is, since pi is surjective, obviously the quotient map is surjective, there should be a bijection between all ideals of R dash, which is how we defined it, and the ideals containing M in R. Ideals containing containing M in R. So this should be a bijection. But M is a maximal ideal by assumption. We assumed in the beginning that M is a maximal ideal. And since M is maximal, R and M are the only two ideals of R containing M. So this set has only two ideals. And obviously, though that means since this set is in bijection with all ideals of R bar, which is R by M, that implies R bar has only two ideals, which, and we know that F is a field implies F has only two ideals, and F has only two ideals implies that F is a field, as we proved in the beginning. So this means R bar is a field. So now both of these theorems lead us to something strong, which is I'll move some stuff up. Yeah, let's keep it there. Actually, no. Let's move some more things up. Okay. So the theorem that we get is if theta from R to R dash is a surjective homomorphism, then the following hold. One, kernel of theta being maximal, both ways implies that R dash is a field. And two, an ideal of R being maximal, both ways implies that R by I is a field. So these are two very powerful theorems that we get, which will be used to prove a lot of results, a lot of further results that use maximal ideals. So since maximal ideals form a very special family of ideals, we denote the set of all maximal ideals of a ring by max R. And let us try to find the max R for some uh, special cases of ring. So if F is a field, the only ideals of F are F and 0, as we have emphasized previously. So that makes the maximal ideal of F to be the 0 ideal, since it has to be an ideal that is properly contained in F and that eliminates F from the list. And so the only ideal that remains is the 0 ideal. So for any field we have the maximal, there is only one maximal ideal, and that maximal ideal is the 0 ideal. Now let's let's make it a bit more interesting. Let's try to find maximal ideal of the ring Z. So we already know, as I mentioned before, all ideals of Z are of the form NZ, where N is a natural number, right? So if NZ is a maximal, and this NZ is basically the ideal generated by N, right? So if we consider all these ideals and we have to find the maximal ideals, then it is quite intuitive that the maximal ideals are the prime ideals. So max of Z is equal to all the prime ideals generated by the prime numbers. Because if uh, n is any other ideal that contains this prime ideal, and then we can assume that there exists a prime p naught that divides n, such that p naught is not equal to p1. If p1 if p naught is equal to p1, then both are the same ideal. Then what we actually have is that all the prime multiples, because this gives all the prime multiples 0, p, minus p, 2p, etc. it means that P naught should belong in this, which is actually a contradiction. Contradiction. So there cannot be any proper ideal of Z that contains an ideal generated by a prime number. So the maximal ideal, the set of all the maximal ideals of Z are precisely those ideals that are generated by prime numbers. Okay, so P such that P is prime. So this is precisely the maximal ideals of Z. So this is one last theorem I intend to prove for the day. And after this, I think I'll define prime, the notion of a prime ideal. And, and then we can see some interesting things about the prime spectrum of a ring. So the last one, if F is a field, if F is a field, let R denote the ring of all polynomials over that field. Then we have the maximal ideal of R is equal to, this is a rather tricky one. It is all the ideals generated by a single polynomial that belong to Ft such that Ft is monic irreducible in F. And the proof for this will rely on the fact that F is a PID, which we will prove. So let's begin this one. So first we claim that F, or rather Ft, is a PID. So although I think you were introduced to what a PID is before, let's just recap. So a principal ideal is an ideal generated by a single element. Principal ideal is an ideal generated by a single element. So a PID, also known as a principal ideal domain, is a family of integral domains. So PID, oh, that's a bit too close. PID is an integral domain such that every ideal, yeah, every ideal of the domain is a principal ideal. And an example that you just saw was Z. Since every ideal of Z is of the form, is generated by a single integer n. So we first show that f of x, so we first take the claim f of t is a PID. So, okay, we'll prove that. This proof will be rather trivial since most proofs for the existence of a PID rely on the division algorithm, which we now have since f is a field. So let I be an ideal of Ft. We need, so what we need to do is we need to show that I is generated by a single element of Ft. So, so the most natural way to do this would be to go to the polynomial of least degree in Ft. So of course, we can do this since all polynomial degrees are positive integers and the positive integers are well ordered. So there exists a polynomial of least degree in Ft. So let Ft be the polynomial of least degree in Ft. All right. Now we want to eliminate a very trivial case, which is if there exists another polynomial gt in Ft of the same minimal degree, then gt is the same as f of t. So basically, what we want to prove is that this polynomial, this least polynomial, actually, that would be a wrong statement. We want to say gt is equal to some scalar times f of t, where a belongs to f. So we want to show that the polynomials of minimal degree in this ideal all are multiples of each other, just scaled up by a scalar belonging to f. So let us let us say gt is equal to an x bar n plus till a naught, and ft is equal to bn x bar n plus b naught. They have the same degree. Now an bn are not equal to 0 since they are of degree n. What we can do is we can multiply. We have bn gt equal to an bn x bar n plus a naught bn, and an ft is equal to an bn x bar n plus b naught an. But bngt again belongs to this ideal I, and so does this. Since the ideal is closed under addition and subtraction, the difference will also belong to the ideal I. So bngt minus anft will belong to I. But that implies we lose the degree n. The difference is of degree less than n. So what happens is degree bngt minus anft is actually less than n. But this is a contradiction since we assume that the minimal polynomial is of degree n. We cannot have any polynomial of degree less than n belonging to I. So this is a contradiction. So we come to the conclusion that in the sense that we assumed, f of t is the unique minimal polynomial. So now let ht be a polynomial in I in this very ideal. Therefore, the degree of ht is greater than or equal to n, which was the degree of f of t, since f of t is the minimal polynomial. So we can use division algorithm. So by division algorithm, we have that h of t is equal to f of t q of t plus rt, where rt is either equal to 0 or degree of rt is less than degree of f. But f of t belongs to I implies that f of t q of t belongs to I, since I is an ideal. And also from our assumption over here that h of t belongs to I, we have that h of t minus f of t q of t will also belong to I, since I is closed under subtraction. But this is equal to r of t, which implies r of t equal to I mean, belongs to I. But we have two cases for r of t. If the degree of r of t is less than the degree of f of t, if the degree which is equal to n, if degree of r of t is less than n, then we have a contradiction again. because it contradicts the minimality of the degree of f of t. So therefore, we must have Rt is equal to 0. If the remainder polynomial is equal to 0, that implies f of t divides h of t. Therefore, for any other polynomial h of t belonging to this ideal, we have h of t equal to f of t q of t for some q of t f of t. So every other polynomial element of this ideal is divisible by f. So basically, that is the equivalent condition for the fact that I is completely generated by f of t. Therefore, we considered any arbitrary ideal I, and we found that it is generated by the polynomial of minimal degree in I, and it is generated by a single element, thus making it a principal ideal. Therefore, we can say that f T is a PID. So we we have that. So now, okay. So I think I have to add a page over here. Yeah. So now that we have f of t is a PID, we intend to find the maximal ideals of f of t. So let I be maximal in f of t. Therefore, since f of t is a PID, I is equal to the ideal generated by some f of t for some ft belonging to ft. And without loss of generality, since uh, if f of t is equal to an x bar n plus so on till a naught, we have an is not equal to 0, so we have 1 by an, and we actually have the existence of this inverse 1 by n since f is a field. Since f is a field, we can guarantee the existence of this 1 by an. That implies that 1 by an of f of t belongs to this ideal I, which implies x bar n plus a naught by an belongs to this I, which is monic. So if we have such an f of t, we have the monic member of the family also belonging. So, so without loss of generality can come here. Without loss of generality, we may assume f is monic. Now, if f is reducible, that is, it can be split as a product of two polynomials of degree greater than equal to 1, which implies f of t equal to g of t, h of t, then we have that the ideal containing g of t and ft actually belongs to the ideal containing g of t, since ft equal to g of t, h of t. And since g of t is a polynomial of degree greater than 1, g of t is not equal to f of t, since it will not contain 1. But this contradicts the assumption that f of t is maximal, because we cannot have that f of t is contained strictly in g of t, which is then again contained in the polynomials over the field. So this is a contradiction. Therefore, ft cannot be reducible. Therefore, if I is therefore if I is a maximal ideal of ft, we must have that I equal to I is generated by some f of t, and f of t is monic irreducible over x. And that concludes the theorem. The converse can be easily proved. It is elementary and I will not bother proving it here. And the converse is that I'll just state it. If ft is, sorry, if f is irreducible, then ft is maximum in f. So I guess this is a place where we can stop here, although there are certain things that we could not cover today, but they don't number in much. So we can cover them in the next talk on UFTs, etc. So are there any questions?
Uh, could you outline a sketch of the proof where you said that the fraction field of a ring is like the smallest field containing that ring?
Outline a scale. Okay, fine. Uh, 1 second. Okay, so we you're familiar with the structure of the fraction field that we constructed, right? It basically consists of the equivalence pairs. Are you familiar with this structure?
Yeah,
Okay, so now let be an integral domain. As you remember, we can construct fraction fields only for integral domains. So QR is a field containing R. Okay, we know that much. The QR that we constructed is a field containing R. Fine. Now let so what do we want to prove? Let's start with what we want to prove. We want to prove that if F is, sorry for the bad handwriting, if F
that's
is
fine.
some field containing containing oh my god, sorry, containing R, then F must contain Q of R. So this is what we basically want to prove, that this states the minimality of Q of R. So it states
Yeah,
that Q of R is a field that contains R, and if F is any other field that contains R, then F must contain Q of R. So Q of R is not bigger than any other field that contains R, basically. So how do we go about proving this? Okay, so let F be some arbitrary field containing R. Okay, so R is a subring of F. Okay, nice. So now every element of R has an inverse. Okay, so for all R belonging to R, there exists an R inverse belonging to F, so that R inverse equal to 1, right? Okay, so what we do here is that since R inverse also belongs to F, that implies that uh, in F must also contain all elements of the form R1 R2 inverse for all R1 comma R2 belonging to R. So is this part clear so far?
Yeah, this
So
follows from
since
like closure. Yeah,
Yeah, so exactly. It follows from closure. We had one set of elements, which was all the elements of R. We took their inverses, and then we basically went ahead and constructed all the like we multiplied the original elements with the inverses. So we've gotten here so far. So now let's do this. Let's build an injection, xi, from QR to F. And xi and all elements of QR are equivalence classes of the form A by B, where AB belong to R, right? So I should take this above actually. Yeah. So this is the form of all the elements. So I can take xi to go to uh, AB inverse in
yeah,
F.
got it. Hmm.
In F, all you have to do is show that this is injective. Show that this is injective. So if it is injective, then you have QR given by this thing, and you all you did is if you had F, you showed that there is an injective map from QR into F, meaning that the image of this map, if this was the image, it means that F contains a copy of QR. Call
Yeah,
that QR subscript F. So that means that every F always contains a isomorphic copy of QR within it, given by this natural map. So it
yeah,
means
okay.
that QR is the minimal such field. So all
Yeah,
the entire proof relies on the fact that this map that we constructed here should be injected, and that is very easy to show.
yeah. Got it.
Yeah.
Thanks.
So are there any more questions? Okay, I'll wait for a minute then. Okay,